Hello, my dear students. Welcome to the online video sessions. In this video, we are going to discuss about the topic inverse of a matrix. First of all, we can say about invertible matrices. Invertible matrices. Invertible matrix or non-singular matrix. Non-singular matrix. Now, what is an invertible matrix? Suppose A be an n by n matrix. Then if we can find another n by n matrix B such that AB is equal to BA is equal to I, where I is the identity matrix. Identity matrix. Then we can say that A is a non-singular matrix. Non-singular matrix. Okay? One word, non-singular matrix. Non-singular matrix. Okay. So A is said to be non-singular or invertible. A is said to be non-singular or invertible if we can find another B such that AB equal to BA equal to I, where I is the identity matrix of order n. Clear? Of order. If B, in this case, B is the, we can say that B is inverse of A. B is the inverse of A and is denoted by B is equal to A inverse. Okay. So if A is non-singular or invertible, then the inverse can be represented by A inverse this notation. For example, consider a matrix that A equal to 2, 1, 1, 1. This matrix is invertible. This invertible or non-singular. Since we have another matrix B equal to 1 minus 1 minus 1 2. Okay, this is the inverse of A. So A equal to 2 1 1 1 is invertible, since B equal to this is inverse of. Okay, we can verify this by multiplying A with B. AB equal to 2 1 1 into 1 minus 1 minus 1 2. We all know the multiplication. So 2 into 1 is 2 plus 1 into minus 1. That is 2 minus 1, that is 1. And 2 into minus 1 is minus 2 plus 1 into 2, that is 0. That is 2 into 1 is 1, 2 minus 1. And this 2 into minus 1 is minus 2. Okay. Yeah, 2 into minus 1 is minus 2 plus 1 into 2, that is, and second row 1 into 1 is 1 minus 1 into 1. 1 into minus 1 is minus 1. So this is minus 1. And this 1 into minus 1, that is minus 1 plus 1 into 2, that is plus 2. So this is nothing but 2 minus 1 is 1, 0, 0, 1. This is the identity matrix of order 2. Okay, identity matrix of order 2. So AB equal to I2. So in a similar way, we can prove that BA equal to is also equal to I2. So we have AB equal to BA equal to I. So B is the inverse of A. So we can say that B equal to A. Okay. Now, another important result is not every non-zero invariant matrix has an inverse. Okay, there is no guarantee that all the matrix has an inverse. Okay, every matrix has an inverse, which is no guarantee for that. Okay, so as a note, we can write not every matrix, not every matrix is actually is non-zero matrix. Okay, not every non-zero matrix uh, of order n or any order. Okay, as an inverse. Okay, not every matrix. So there is no guarantee that every matrix has an inverse. Okay. For example, we can say let A equal to the matrix 1 1 a simple matrix 1 1 0 0 0. This matrix A has no inverse. Since suppose that for this has no inverse or this is not invertible. Okay, matrix has no inverse or A is not invertible. If possible, suppose that A is invertible. Okay, uh, if possible, suppose that A is invertible and that B equal to A inverse. A is invertible means A has an inverse and let B equal to, or we can write this is equal to A inverse is equal to B, which is equal to some A, B, C, D. Okay, then since this is the inverse, we can write, since B is the inverse of A, then we have AB is equal to BA equal to I. So we are checking this. Now AB is equal to, we have A is 1100 and B is ABCD. So this is nothing but by multiplication of the matrices. We have 1 into A, that is A, plus 1 into C, and 1 into B plus 1 into D, that is D, and 0 into A plus 0 into C, that is 0, 0 into D plus 0 into D, that's also 0. Clearly, it is not equal to the identity matrix A. Identity matrix is 1001. It is not equal to, this is the identity matrix, but clearly this matrix is not the identity matrix because this term is 1 and A plus C cannot be equal to B plus D not equal to, we can find this matrix such that B plus D equal to 0. So it has this matrix A has no inverse. That means A is not invertible. Okay, so therefore A has no inverse. That is A is not invertible. Okay. Next, uh, if if the matrix A has no inverse, then A is said to be singular. A is said to be singular. Okay, this is important. So A is said to be singular if A has not inverse. So no, non-singular means A has the inverse or invertible. So we have non-singular and singular. Non-singular means invertible matrix. Non-singular matrix means invertible matrix. That means uh, if A has inverse. If A does not have an inverse, then it is said to be singular matrix. Okay, if A has no inverse. Okay, next the another result is if A has an inverse, if the matrix A has an inverse, then it is unique. Okay, so I am leaving the proof of this result to you. Uh, I think you already proved this in the low classes. So you just prove this and submit as in the notebook. Okay. Then next properties of the inverse. Properties of inverse. Okay. Now first property is, suppose let A and B be non-singular matrices. Non-singular matrices. Non-singular means invertible matrices. Okay. Non-singular or invertible matrices. Then we have the properties. First one is uh, A inverse is equal to A itself. That is the inverse of the matrix A. That is A inverse. It's also invertible and its inverse is A. Okay. That is if here we have A is the non-singular matrix, that is invertible matrix. A has an inverse, and then we can prove that A inverse also has an inverse, and the inverse of the A inverse is A itself. Okay? Now the second property is AB inverse is equal to B inverse into A inverse. B inverse into A inverse. In general, we can prove that general we have for A B C inverse is equal to C inverse, B inverse, A inverse. If we have A B C D, there are matrices, then A B C D inverse is equal to B inverse, C inverse, B inverse, A inverse. So the inverse of the product of matrices is the inverse of the product of their individual inverses in reverse order. Okay, it can be extended into finitely many uh, product of matrices. Okay. Now third is we have the transpose of a matrix. So the inverse of the transpose is nothing but A inverse transpose. That is the operation transpose and inverse can be interchanged for a matrix. Okay. Okay. I will prove the first one and I will leave the second and third to you as a homework. Okay. Now the first case is A inverse. We have to prove that A inverse of A inverse whole inverse is A. That is, we know that the definition of the inverse, that is A B is the inverse of A if AB equal to BA equal to I. So to prove that, to prove the first one, that is to prove A inverse of inverse. Okay. Uh, First one, to prove the first one, uh, to prove that we have to prove that A inverse of A inverse all inverse is equal to A. It is enough to prove that. It is enough to prove that uh, A into A inverse is equal to A inverse into A, which is equal to I. Okay. We have to prove that the inverse of A. So inverse of A is equal to this. Okay, we already know from our directly we'll get this from our definition, because we have by using the result we have B is the inverse. Then if AB equal to BA equal to I, then we can say that what B is the inverse of A. So to prove this, we need to use this only, because inverse of A is A inverse. So from this we get uh, here A into A inverse equal to A inverse into A equal to I. So from this we have or can write, since this is, can write since A is non-singular, we have implies A inverse exists. Okay, so we have A into A inverse is equal to A inverse into A equal to I. That means we have A inverse into A equal to A into A inverse, which is equal to I. That means A inverse is the inverse of A and A is the inverse of A inverse. Okay? That implies A is the inverse of A inverse. That is, we found a B such that B equal to A here. Okay, is that A inverse into B equal to B into A inverse equal to I. So we can replace our B in this case by A here, right? So A is the inverse of A inverse, plus A inverse whole inverse equal to A. Okay, that is the first case. Now you just do the second and the third. Okay, you know the properties of matrices. So just find this directly. You can write AB inverse into, if we need to prove this, AB inverse is equal to B inverse into B inverse into A inverse. You just multiply AB with the B inverse into A inverse. Okay, so you will get, or I can do this really like this. AB inverse, sorry, AB into B inverse A inverse. This is nothing but A into, by associativity, B into B inverse into A inverse. This is nothing but A into B inverse is I into A inverse. Since B is invertible, we already have B into B inverse is I. So this A into I into A inverse, this is nothing but A into A inverse. That is, so AB into B inverse A inverse is equal to I. Similarly, we can prove that. Similarly, we can prove that uh, B inverse A inverse into AB is equal to I. Okay. So therefore, we can say that the inverse of this AB is, therefore AB inverse is equal to B inverse A inverse. Okay. So now third, you just do that. Okay. Next property is how to find the inverse of a matrix. Okay. You already know that we have a theorem. Let A be an n by n matrix. Let A be an n by n matrix such that determinant of A is not equal to 0. Then let A be an n by n matrix such that determinant of A not equal to 0. Then uh, A inverse is equal to adjoint of A divided by determinant of A. This is the, we already know this formula. Okay. Uh, we know in a 2 by 2 case, if A equal to A, B, C, D such that the determinant of A is not equal to 0, then A inverse is equal to the adjoint of a 2 by 2 matrix is B minus C A, now divided by determinant of A. Okay, determinant of A. So we're just interchanging this. You know these things, interchanging the diagonal elements A and B, and just revising the sign of the off diagonal element. So we have the A inverse of a 2 by 2 matrix and do like this. So you know the method of finding adjoint. Adjoint of a matrix A is the cofactor, the transpose of the cofactor matrix. I think you know that. So I am giving you some two problems. You just find question one. Find the inverse of the uh, matrix, following matrix A, and verify that A inverse is equal to A inverse A is equal to I. In first case is A equal to the 2 by 2 matrix 1, 4, 2, 10. Okay. Now the second question is the 3 by 3 matrix A is equal to 2, 2, 0, minus 2, 1, 1, 3, 0, 1. Okay. So you just find the inverse of these two matrices by finding the adjoint. Okay. So this method is called the adjoint method. You know to find the inverse of a matrix by using the adjoint. Okay. So this I am leaving this as a homework. You just find the inverse and and verify this a into a inverse equal to a inverse into a equal to. Okay. Next we have a theorem. We have a theorem. An n by n matrix, an n by n matrix A is non-singular. Non-singular means invertible. Non-singular if and only if determinant of A not equal to 0. I think you all know this. Determinant of A not equal to 0. Now how to prove this? How to prove this? Okay. That means the matrix A is non-singular implies determinant of A not equal to 0, and determinant of A not equal to 0 implies A is non-singular. Okay. Now the first case, suppose that determinant of A not equal to 0, then we have inverse of A, that is A inverse is equal to adjoint of A divided by determinant of A. This is exists. This, that is A is invertible. Directly you get this. This is by the previous theorem. So A is invertible or non-singular. Non-singular. So we proved a determinant of A not equal to 0 implies A is non-singular. Now the reverse direction is we suppose we need to suppose A is non-singular and we have to prove that determinant of A not equal to 0. Okay. Now how to prove this? Suppose we have conversely suppose that uh, A is non-singular. is non-singular. Therefore, we have A has an inverse. To show that, we have to show that what? Determinant of A is not equal to 0. This is we need to show that. So, since A is non-singular, we have A has an inverse. A has an inverse A inverse, right? Since A is non-singular. That is, we have A inverse is equal to A inverse A is equal to I. Okay. So from this we have determinant of A inverse is equal to determinant of A inverse A is equal to determinant of I. Okay. So but we know that determinant of I is equal to 1. Okay. From this, determinant of A inverse is nothing but determinant of A into determinant of A inverse. Okay. You know that determinant of AB is equal to det A into det B. So this is equal to det A inverse into determinant of A, which is equal to determinant of I is nothing but 1. We know that the determinant of the identity matrix is 1. So from this is not equal to 0. So determinant of A not equal to 0. We think that implies determinant of A not equal to 0. Okay, otherwise if determinant of A equals 0, then this is equal to 0. So determinant of A not equal to 0. So we have proved that uh, the matrix A is non-singular implies a determinant of A equal not equal to 0 and the vice versa. Okay, so and that's all for today. Thanks for watching.